Hey there, everyone. We're back to continue our discussion on resonance. Today we're going to look at parallel resonance. Just to remind you a little bit about what we talked about in series resonance. Resonance occurred when the capacitive and inductive reactances were the same. They basically cancel out, and in a series circuit that leaves us with just the resistance. This is a minimal value. Consequently, we get a peak in current at the resonant frequency. We defined how tight that curve was in terms of its Q, or quality factor, which can be found via the F1 and F2 frequencies, in other words, the half power frequencies on either side. The difference between those gives us the bandwidth, and the ratio of the center frequency to the bandwidth gives us the Q. It can also be defined in terms of the inductive reactance and the resistance in the system, X sub L over R of system. Parallel resonance is similar in many respects, but there are some very important differences. In this case, we're going to start with a current source feeding an ideal system consisting of a resistor, an inductor, and a capacitor. Now, as in the series case, we will still say that resonance will be achieved when the magnitude of X sub L is the same as X sub C. It will still be the case, again ideally, that F0 will equal 1 over 2 pi times the square root of LC. All right, now remember what these impedance versus frequency plots look like. All right, so here's X. All right, so X sub L, looks like this. All right, meanwhile, X sub C does something like that. Right? Our resonant frequency is going to occur where those are the same. Here's where things get a little bit interesting. In the case of the series resonance, right, we would consider R, L, and C in series, this sort of arrangement, in which case we can see at low frequencies, right, X sub L is minimal, and X sub C is a very large value. So the end result, of course, would be largely capacitive. The exact opposite happens at high frequencies. Right? Cap basically shorts out, X sub L dominates, and we have this U-shaped impedance curve. All right? With this, we see the opposite situation. Right? Because they're in parallel, what ends up happening is at very low frequencies, X sub L is a small value. So it essentially shorts everything out, and we get a small value rather than a large value in the series case. If we then go to the high frequency end, we see the same thing happening with X sub C. That basically shorts out everything. Okay, so we have a small impedance over here, small impedance back here. In the middle, basically the X sub L and the X sub C cancel out. But in the series case, where that leads to 0, in the parallel case, that leads to infinity. Right? If you just think about the product sum rule, if you said, hey, I'll find the parallel combination as JXL times negative JXC divided by the sum, right? JXL plus a negative JXC. Now what we see here is the frequency approaches F0. The denominator here does what? It approaches 0. These things cancel, which means this result approaches infinity. And what we would be left with in that case is just the value of R. You'd have R basically in parallel with this pair, which is approaching infinity. So the impedance of this does something along this line, comes up to a peak and then drops off, right? So this is your center frequency, your F sub 0. What is this peak value, right? What is this guy over here? Well, that is the value of R, the total R that we have in the system, okay? All right, now given that, and given that we're driving this with some current source, right, some value I over here, the voltage across this will echo this shape. In other words, we'll get something as a voltage that looks like this. Comes up to a peak and then drops off, right? And again, there's the F0. So this is the voltage across the parallel network. We would find the F1 and F2 the same way we did for series. In other words, those are the half power points. So here's F1 over here, here's F2 over here. Okay, so that would, in this case for a voltage, this would be roughly 0.707, 1 over the square root of 2 times the peak value that we would have at the center, at the peak over here. Okay? All right, so that voltage would just be the current value times whatever R happens to be, because that is our peak value. So this voltage right here is just I times whatever R is. All right? It would still be true that bandwidth would be defined as F2 minus F1. Right? That doesn't change. We would still refer to the Q of the system in terms of the F0 and the bandwidth. And it would still be true that we could approximate, again, at least for high Q, F1 as being F0 minus the bandwidth splitting in half, right? Half on either side, and F2 as being F0 plus that same piece, right? So this is true for high Q stuff, all right? Same exact thing that we saw in series, right? That works fine. It's still true, by the way, that Q of coil would still equal X about L divided by R coil. Right? And that brings us into something interesting, which is, this is an idealization. In the real world, we don't see something quite like this. Instead, we really see something closer to this. We have our current source, here's the resistor, and the inductor really has an R coil associated with it. Okay, so there's our XL and there's our R coil. Well, this is not a parallel network, right? This is a series parallel network. We can't just ignore this R coil in many instances. As a matter of fact, this, in many circuits, will be a major determining factor in the overall performance of this. In other words, do we wind up with a very tight, sort of high Q kind of circuit, or a much more broad, low Q kind of circuit, right? Again, the Q system versus the Q coil. The Q coil could play a role in here, just like it did in the series case. How do we solve this little problem? Well, the basic way of approaching this is to do a series to parallel transform. In other words, we take what we have as a series, right? We have some XL here, and we have some R coil. And we want to turn that into a parallel equivalent, right? A mathematical equivalent that looks like this, all right? Some equivalent XL, some equivalent R value. Well, for high Q, we can make some approximations. Now, there's an exact treatment of this in the text that we're going to basically approximate here. So if you want to see the exact value, go to the text and you can see the proof of this. But for high Q, here's what winds up happening. The XL is basically unchanged. All right, and if you've forgotten, by the way, high Q generally means 10 or more, although this will actually still work pretty well if you had a Q of like 5 or 6. You really only start to see large deviations when we get to, really pretty small Q values, like 3 or something like that. The R value here, I'm going to call this RP. And it turns out that this RP value, right, RP for parallel, is basically equal to the Q coil times the XL. Now, remembering that XL, right, going back over here, can be found as Q coil times R coil, we can say that this parallel value is equal to Q coil squared times the original R coil. So what this means is that if we have a really small value of our coil, in other words, if we have a high Q coil, right, a high Q coil is big, what that means is we get a really big value for RP. Now you might think, wait a minute, didn't you just say a small R coil? How do I get a big value here if this is small? Well, remember, Q coil is the ratio of XL to R coil. So if I were to drop R coil, let's say I cut it in half, right? This term's half as big. But when I come over here, I cut this in half, Q coil doubles, and Q coil term is squared, right? So I cut this in half, this thing goes up by a factor of 2, which is squared 4, RP's 4 times the size, all right? So when we think of the idealization here, as Q coil would increase, as it would approach infinity, R coil would approach 0, which means that RP would approach infinity, which is what we were talking about back here. Right? We've got an ideal coil. In other words, we're back to the first circuit. So the smaller the value of our coil, in other words, the better the coil itself, the bigger the Q coil is, the bigger this RP value winds up being. So we can now take this RP value and we can combine it with any other resistance value that we have to come up with a completed circuit. In other words, we wind up with something that would look like this. We would have our current source, we would have, whatever circuit resistance we began with, and then we would have this RP thrown in here, our converted value, transformed value. We'd have the transformed X value, which is basically XL, and then of course the capacitor, right, X sub C. All right. Here, obviously, we can combine these two things together. They're in series, so let's just call that RT or R total. And we basically have the original circuit with some slightly different names. Now, there's a very important thing to note here. The opposite characteristic of series resonance. Right? What we see in terms of defining the system Q is flipped. A small R coil gives us a very big value for RP. It increases the R total. So that ratio for finding the Q system is also flipped. Instead of saying, oh, this is going to be just a ratio of my XL over my total R, now it's the total R over the XL. Right? So again, if you think back, if you forget this, if you think back in terms of the idealization, our total would be infinity. So the Q system would be infinity. Right? That would make perfect sense. Right? So that's a little memory aid that you can use. Right? So again, it's inverse of what we see in the series case. Right? So in a practical analysis, what we might have is for this current source and this R value, this might be something like a model for a transistor, modeled as a current source with some internal, maybe biasing resistor associated with it, an output impedance of the amplifier. And then this over here would represent perhaps a tuned load, in other words, an LC network that we were going to drive. So I could make a tuned amplifier that had the best performance at a certain narrow range of frequencies. All right? Okay, so very important point here that that's flipped. Right? Another thing that I want to indicate is what's going on over here in the non-ideal high Q case. Right? When we go to lower Qs, this approximation that x sub L stays the same, that goes away. The x sub L actually shifts with frequency. All right? When we get a small Q, you get a Q of like 3 or 2 or something like that. The x sub L in the transform circuit is different from what it was in the original circuit. And that causes the critical frequency to shift. Basically what you wind up with is the original value, the 1 over 2 pi LC, square root of LC, times some coefficient K. And there is a formula, actually 2 formulas in the text that derive out what the value of K would be. This is a fractional value, so you end up with a frequency that's a little bit less than calculated. The reason why there are 2 of them is because there's 2 different ways you can, in fact, define where your resonant frequency is. In the series, or the ideal case, they happen to be the same, which is A, where the impedance peaks, or B, where the phase shift goes to 0. All right? Now, in this circuit, the phase shift here is flipped compared to what it is in series. Because, again, if we were to look at a low frequency, x sub L dominates, so we have an inductive phase angle. We go to a high frequency, the cap shorts out, that dominates, so we have capacitive angle, opposite of what we see in the series case. But either way, at resonant frequency, at F0, it should be an angle of 0. So those are basically 2 different ways of defining it. Where do we get the impedance peak? Where do we get the 0 phase angle? You could also refer to the 0 phase angle as being where is the power factor unity. So there's 2 different ways of doing this. When we get to lower Qs, those 2 things are no longer really the same. They start to deviate a little bit. All right? Is this a huge problem? To be honest with you, no, it's not usually a huge problem, because the whole reason we use tuned circuits is to get the selectivity. In other words, we don't really want broad Qs. The whole point is to sharpen these things up so that there is a narrow range of frequency, whatever the bandwidth here is that we need. So I don't really normally want a circuit with a Q of 2 or 3. I'm looking for much, much higher values, double-digit values for that. That's typically what we're looking for. Okay? All right. Now, the last thing to consider is, you might remember in the series case, it was possible to get voltages across the reactive components that were much, much bigger than whatever your source voltage happened to be. Right? Because again, at resonance, the x sub L, the x sub C can be many, many times bigger than whatever R is. That's the Q system. Well, in a parallel circuit, the voltage is the same everywhere, so that's not going to be seen here. However, we see a similar sort of thing happening with the currents. Right? At resonance, when we look at the Q system, right, the x sub L value and the x sub C value can be much, much smaller individually than the R value. If we had a Q of 10, nice round number, but what we're basically saying is that the x sub L value, the x sub C value, are both going to be 1/10 of whatever R is. Well, they all have the same voltage, right? It's a parallel circuit. So what does that mean? That means the current through these 2 branches are going to be 10 times higher than what we would see through the resistor. But of course, they're 180 degrees out of phase. So what does that mean? Kirchhoff's current law says, look, what's coming into this node, right, this current coming in here, that's going to split 3 ways. Right? Simple reference directions. But these 2 things are actually in anti-phase. When the current's going down in the inductor, it's going up in the capacitor, right? We have signs. Time for a new pen. We have something that goes like this. That could be the current for the inductor. Meanwhile, the current for the capacitor would be doing something like that. Same magnitude, but they perfectly cancel each other out. So if you had a 1 milliamp current source coming in here, right, that 1 milliamp is going to go down through the resistor, but you're going to get, in this case, 10 times that, 10 milliamps, through these 2 reactive components, but it'll be in this sort of phase relationship. So KCL works out just fine, right? The summation coming in is equal to what's coming out, because these 2 things basically sum to 0. This section right in here is sometimes referred to as a tank, T-A-N-K, a tank network. Tank current, we think of sort of current as bouncing back and forth between these two reactive components. The tank current is basically Q times higher than whatever your source current is, right? So this is sort of the analogy, the mirror, if you will, to the series case, where the voltages, the reactive voltages, can be Q times higher than the source voltage. Here we're talking about those currents, right? The magnitude of the capacitor and inductor currents, right? The magnitudes of these things are basically Q system times, whatever your source current is. Yeah, so if we have, a system Q of 50, and this is 100 milliamps, well, you're going to get 50 times 100 milliamps, right? So you're looking at 5 amps of current, flowing through there. Quite possible. Seems a little crazy. You could have a milliamp source, and you're getting amps of current out here, but that's the way it works out, right? So something to watch for. If you mock up something like this in a lab, okay? All right. We'll continue this next time. We'll take a look at an example, with some nice hard numbers, and we can see exactly how this all falls out. All right? There you go.